current carrying loop. It is rectangular in shape. This is the current carrying loop. It acts absolutely like bar magnet or magnetic dipole. When we place this current carrying loop in the magnetic field, in the external magnetic field, so this is known as the space in between these two poles. These two are permanent magnetic poles. This direction indicates direction of the magnetic field, external magnetic field. If we place this loop in the external magnetic field, it gets rotated about the axis. It gets rotated about its axis. This rotation is due to the magnetic forces arising at the conductors, which is in turn due to the interaction between the two magnetic fields, that is magnetic field by itself and the external magnetic field. Let us look into the forces and the resultant of the forces, which finally gives rise to the torque force, that is rotational force. In this loop there are four conductors. So I can call this line as one conductor. This is second conductor, the third conductor and the fourth conductor. Whenever a conductor that is in straight line is placed in the magnetic field, external magnetic field, as you know, it produces Lorentz magnetic force. It is given by Lorentz concept. That magnetic force is given by the equation. The equation is this equation. The magnetic force which is acted on the conductor due to interaction with the external magnetic field is given by this equation. Recall this equation. This equation is F equals I BL sin theta. I stands for the strength of the electric current in the conductor. B is the strength of the intensity of the external magnetic field that is applied. This is the external magnetic field direction from this point to this point. And L is the length of the conductor. The direction is the current direction, like this. That is the magnitude of force, some pushing force on the conductor. It is given by this equation. Let us estimate using this equation what amount of force on this conductor as well as on this conductor, on this conductor and this conductor, where theta, sin theta is there. Theta is the angle between the line B and the line L. Here the line B always in this direction. Line L, look at this is the direction of L with respect to this line. Direction of L with respect to this line. In this conductor, it is a line, direction of the line, direction of the line. Angle between B and L. Let us estimate the force exerted on this conductor as well as on this conductor using the same formula. IB L sin theta. What is the theta? What is the theta when upon this line, on this line? Look at this line and the current direction. It is same as this line. This line and this line are parallel in the same line, same direction. That is theta equals 0. If theta equals 0, sin 0. Sin 0 means the sign of the function is 0. 0 and anything is 0. The force acted upon by this conductor due to this magnetic field, that is a 0. Sin 0, 0. Similarly, we can calculate the F that is exerted on this conductor. This line is in the same line, but current direction is this. See that the line direction and this line direction, they are in the opposite direction but in parallel. If that is the case, the angle between this line and this line is 180 degree. So on this conductor, that is the force acting 180 degree. So 180 sin 180 is again 0. 0 into this is 0. And the length of the conductor, whether the conductor here is A is a length, A is a length, opposite sides. And this B and B, the lengths of these conductors. So the force at this, on this, the force at this conductor is 0. Let us calculate the force exerted on this conductor in the same formula. So look at this line and this line are perpendicular to this line, that is sin 90. Sin 90 means 1. 1 into this is a 1. IBL. Here it will not become 0. IB into L. What is L? Length of the conductor. Length of the conductor is B. Sin theta. IB, where theta is 90 degree. So it varies between 0 and 90. When 0 it becomes 0. But in this case it is not 0. With some degree or 90 degree, it has some value like this. So look at this force. Here IB, current strength in all the conductor remains same. Here with respect to the conductor 2, this is the conductor 2, this is the conductor 4. B is the length, current is high, current is high. In all the conductors, current strength is high. And IBB, sin theta, both of them. So F is equal to IBB sin theta. This is the one. And what is the direction of force? Force is exerted, force is exerted. What is the direction? The direction of force using what is that? Right hand palm rule. Recall that right hand palm rule. What is right hand palm rule? You have to hold your right hand like this. Here, so this in the direction of the magnetic field, all the 4 fingers, and this should be in the direction of the current, So if you hold my right hand like this, in the coinciding with the directions of the magnetic field, this is the magnetic field direction and this is the current direction. And the palm facing what is that? This side. The palm facing in this direction. So this should be the direction of the force. Inward direction. It means it is perpendicular to the board, perpendicular to the line, but inward direction, in the backward. Force is pulling in the backward direction. That is the direction, inward direction. What about the current direction is reverse. Here current direction is this. same force is acting here because length remains same and height remains same, B remains same. Direction, what is the direction of the force? Same apply, apply the same rule. That is, you have to hold it like this. Direction of the magnetic field and direction of the current. If that is the case, it is facing in this direction. Likewise, it is facing perpendicular to the board but outward direction. That's the outward direction. At this point, outward direction, at this point, inward direction. Both forces are same, but in the opposite direction, but not in the same line. They are separated by a distance. This is a perpendicular distance. The distance, of course, is A. So there are two equal forces acting in the opposite direction, not in one line, separated by a perpendicular distance like this. The same case. Here, couple of equal forces. This couple of equal forces produces a torque force. That is a rotating force. That is the reason the net force, here force is 0, force is 0. The resultant of these two forces, the torque which will rotate, in this case what is that? Here this side is pulling backward, this side is pulling up in the, what is that, in the forward direction, and gives rotation about the axis, clockwise rotation. It will be rotated in the clockwise direction. That is called as torque force. So what is the torque force? Definition of torque force. The torque force acting on this loop, rectangular loop, is the force. You can take any one of the forces. Both forces are same. And the perpendicular distance between them. That is a perpendicular distance. A is a perpendicular distance. The force acting at the point is IBB sin theta. The force is IBB sin theta. L stands for B. B stands for L of the conductor. Both the conductor's length are same. So you have to simplify. This is what is the torque force. The net torque force on the loop, rectangular loop. Now I simplify. This is A into B, IB sin theta. A into B. What is A into B? Length into breadth of the rectangle. It is the area of the loop. Here the loop is rectangular. Area of the loop. This into this gives area of the loop. Replace this by A. Capital A represents area of the loop. B is the magnetic field strength, external magnetic field strength. What is I? Current in the loop. And theta is the angle between, now the angle between A into B. Now what is A and what is IA? Recall this definition, mathematical definition. Current strength into area of the loop is M. What is M? M is the dipole moment. Dipole moment of what? Magnet. This is magnet. Magnetic dipole moment of the loop. Magnetic dipole moment of the loop. M. So replace I by M. Torque equals M into B into sin theta. Look at the terms we have. What is M? Magnetic dipole moment. Magnetic dipole moment of the loop. B is the external magnetic field into sin theta. Theta is the angle between M and B because M has a direction. Recall that how do you find the direction of M in this current carrying loop? Again, the right hand rule. That is, in the current carrying loop, what is that? This is the current carrying. You have to hold your hand like this and push the fingers like this in the direction of the current in this, what is that? A loop. So if you hold your fingers and push your fingers, wave your fingers like this. This will indicate the direction of M. It is. So it is perpendicular to the plane and outward. This is the direction of the M. So direction of the M is like this, perpendicular to the plane of this. If this loop is in the, what is that, in the same orientation as written here, the plane is on the board. For this plane, the magnetic dipole moment of this loop is this direction. So this direction and this direction, this is the direction of B, are perpendicular in this orientation. So theta is the angle between M and B. Theta is the angle between M and B. So rewrite this as M such value M into B, vector M, vector B, cross product of vector. The total torque, the torque force produced by this current loop is magnitude of the dipole moment by this loop and magnitude of applied magnetic field, the torque force, final equation. So if this is the alignment, what is that? Orientation of this loop. Orientation of loop. What is the orientation of the loop? The loop, plane of the loop is on the plane of the board. Produces the torque force like this. Let us find out the torque force. By this force it is rotated. Suppose if you rotate